In the previous two lectures on connectivity, we were primarily focusing on legacy protocols which have been around for offering industrial communication of high quality, high grade, having specific industry specific requirements of reliability, low latency, low jitter and so on. But there are many different protocols that could be used in the industrial contexts. Many different protocols have evolved over the years. Particularly with the advent of wireless communication, low power wireless communication, IoT based communication and so on. So, if we look at present we are talking about industry 4.0. So, industrial revolution has happened through different generations of 1, 2, 3 and at present we are talking about 4.0 where the focus is on connectivity. Now, in this particular context, there are different IoT technologies that have come up which can help cater to the requirements of supporting industry 4.0. Protocols such as the ones that we have discussed in the introductory section on IoT. At the outset of this particular course, we talked about different IoT protocols such as AMQP, MQTT and many others that we have gone through so far could all be used in addition to these legacy industrial communication protocols that we have discussed in the previous lectures. In addition, we could use different other advanced protocols, particularly protocols belonging to different wireless communication technologies could be used in order to provide connectivity between different devices such as the industrial machines, different types of industrial machines, robotic machines, robotic devices, between security cameras in the industry and so on, and supporting different quality of service parameters of the networks that are being built in terms of delay, availability, reliability, throughput and so on. Overall, what is desirable is to have unified connectivity even if you are using an assortment of different protocols which may be wired or wireless or which could be the legacy ones or the modern ones. What is important is to be able to offer unified connectivity. Unified connectivity means what? That seamless connectivity. Users would not know how which protocol depending on the specific requirements, scenarios, instances, circumstances and so on, which protocols are being used and they are basically getting shuffled, reshuffled and so on at the back end. Users basically get the services and behind the scene there is an unified connectivity architecture that basically helps in sending data from one point to another, catering to the specific industrial requirements that are there. So, these legacy protocols have been there: Modbus, TCP, RTU, these field bus, Profibus, Interbus and so on. So, all these protocols have been there. Plus you have new protocols such as MQTT, AMQP and many others which have become popular in the IoT era. Plus there are few others that we are going to discuss now, which are like 5G, tactile internet etc., which have become very popular in the recent times. They could also be used, they could be integrated together to offer an unified kind of platform supporting different protocols. They could be used and unified connectivity can be offered. What is next important is the optimized service. Optimized service, dedicated network communication, low latency communication, ultra reliable communication, these are the different other industry specific requirements that will all have to be catered to. So, this low latency communication is understood, ultra reliable communication is also understood. What is this dedicated network? Customized requirements. Basically, customized requirements will have to be fulfilled in addition to the, because different industry, particularly different industrial sectors have specific customized requirements. Those dedicated network solutions will have to be used in order to fulfill to the customized requirements, plus optimized together with fulfilling these customized requirements, optimized service offerings will have to be made. So, we will look at different protocols. There have been different community initiatives, for example, the 3GPP, which has different releases catering to industrial requirements, is this release 15. Release 15 basically caters to the industry specific requirements. Release 16 basically talks about the factories of the future, so smart factories and so on. So, different use cases supporting the factory smart factory requirements. And then you have the 5G ACIA, which basically unites the OT industry. OT means operational technology industries with the ICT industries, information and communication technology industries, and academia for enabling 5G for industries. So, basically this is talking about 5G for industries, 5G ACIA, and IEEE has different protocols like the TSN supporting the 802.1q Ethernet protocol. So, 3GPP release 16 has these different use cases, has support for different use cases. These are the ones that are basically listed in the 3GPP document. So, first one is the support for rail bound mass transit, building automation, smart healthcare, smart city, factories of the future, smart farming, centralized power generation, electric power distribution, program making and special events. These are the different use cases that are supported by the 3GPP release 16. Factories of the future. Here basically we are talking about catering to the heavy industries primarily, such as oil refineries, mining industry, manufacturing industry, warehouses and so on. And the interests of the different systems, for example, motion control, this is very important, robotic machinery, sensor networks, massive wireless sensor network deployments, all of these are requirements specific to the smart factories or the factories of the future. So, 5G technology could be used to build different private networks within these different industries. So, there is this 5G NR, 5G new radio, which has different band specifications. This high band, which is basically more than this 24 gigahertz band, is this supports millimeter wave communication, Then we have this for small scale private network communication, small cell deployments are also there in the form of femtocells, picocells, integrated Wi-Fi and so on, plus this device to device communication. So, basically you are talking about one device supporting one type of cellular communication with another device supporting another cellular communication, not another, but the same cellular communication, basically device to device direct communication without involving some kind of a centralized controller is going to be performed, and that is sometimes required. And this will be very much useful, particularly in the industrial context, because one machinery might want to talk directly to another machinery, and you do not want to send the packets from this machinery to the central controller and then from the controller to the other machine. So, device to device communication will cut down on the overall latency of communication in the system. So, let us talk about this 5G NR. So, it provides, it is a 3GPP protocol which provides new air interface and is aligned with different ITU service categories such as the enhanced mobile broadband eMBB, massive machine type communication MMTC, and ultra reliable low latency communication URLLCC. So, the design objectives are to offer backward compatibility. That means connecting different devices which with the help of these technologies plus the technologies that were supported in the past. So, backward compatibility will be supported by these different technologies, and also enabling versatile connections across different heterogeneous devices produced by different vendors, supporting different standards, and small device, large devices supporting different speed, maybe PC to PLC, PLC to PLC to something different, a high motion device with a small low motion device, and so on. So, all these different types of heterogeneous communication could be supported with the help of this NR. Small scale deployment, here we are talking about addressing different objectives such as alleviating burden on the backhaul, improving energy efficiency, and decreasing the dead zones. Dead zones are basically the ones where there the network the signals basically do not reach. So, if there are some dead zones where the signals do not reach, the small cell deployment will help in this kind of offering connectivity in those dead zones where the signals are not able to reach. So, operating frequency, these small cells support both licensed spectrum as well as license exempted spectrum. So, it can be supported by both of these types of spectrum. And device to device communication, here we are talking about this kind of thing. So, machine 1, machine 2, they can talk to each other, D2D link. Again machine 2 to machine 3, another D2D link, device to device communication, that basically cuts down on the time or the latency of communication and so on. So, these are the D2D links, this is one, this is another, and we are talking about it in contrast to the traditional links. Traditionally what would happen is the machine 1 would send the data to or the packets to the access point, and from the access point it is going to come to the machine 2. So, instead of doing a roundabout kind of way, this direct machine to machine communication takes place. So, the overall objective is to reduce the latency, increase throughput, and eliminate load onto the backbone network, the core network. This is very important now. A technology which has become very popular is the tactile internet, which basically supports data transmission in the context of touch, offering real time transmission of touch sense devices and actuating them, right. So, provides a new facet to human machine interaction, particularly in the context of HCI, BCI, etc. This tactile internet has become very popular. Haptic communication, it provides haptic communication enablement, supports low end to end latency of less than 1 millisecond RTT. Haptic communication architecture is given over here. So, we have this human interface, this is this human interface, we have these remote machines, and in between we have this tactile enabled core network, and this overall haptic communication architecture is shown over here. So, for more details you are encouraged to look at this particular paper which is talking about towards haptic communication over the 5G tactile internet. So, haptic communication over 5G tactile internet is talked about in this particular paper. So, I would encourage you to go through this particular paper to learn more details about how these mechanisms work. So, in terms of fulfilling requirements of ultra responsive connectivity, latency in the order of 1 millisecond, ultra reliable communication, ubiquitous connectivity, wide range of coverage, security, privacy, tactile data exchange, edge intelligence, that means close to the source of the data, some of these processing is going to be done instead of sending everything to the back end to the servers and so on for further processing. So, edge intelligence, close to the edge, that means the source of generation of the data are going to be performed with tactile internet. So, there are different ways to realize the tactile internet. SDN is heavily used, SDN technology, MIMO, MEC, mobile edge computing, and network function virtualization. Applications for use: industrial automation, autonomous driving, robotics, healthcare, virtual reality, augmented reality, gaming, UAVs, and so on. Next comes this particular protocol URLLC, which is ultra reliable low latency communication. So, as you can understand that this is quite attractive for industrial scenarios. So, here the requirements are to have availability in the order of 99.9999% availability, right. So, the network is made available in 6 nines, 99.9999% of the time it is available. So, high levels of availability. Then end to end latency of in the order of 1 millisecond, reliability in less than 10 to the power minus 5 outage probability, packet size of 30 to 200 bytes and smaller transmission duration. Design challenges. There are different challenges with the traditional communication systems with respect to throughput, latency, TTL and TTL TTI. So, TTI is basically transmission time interval, TTI, then the processing delay, TTI, latency, these are all quite high, including the throughput is also quite high with the traditional communication systems. So, here we need shorter TTI systems which will provide quite faster communication, prompt communication, low latency communication with larger signal overhead. So, basically the signal overhead is going to increase additionally. So, additionally we have to deal with challenges of errors. Dealing with errors, we are talking about error prone challenges which decreases the reliability. And so the different methods are there. Shorter TTIs or shorter TTLs, whatever be it, it is the same thing. So, we are talking about shorter TTL requirements, smaller slot length in micro scale, flexible transmission frame structure, then reducing the orthogonal frequency division multiplexing symbols, reducing symbol duration and so on. So, all of these make it attractive for use in mission critical applications. Fast HARQ retransmission scheme. HARQ stands for hybrid ARQ. ARQ is automatic retransmission request, and basically this fast HARQ is basically takes care of the retransmission through the procedure of predicting the correctness of the received symbol before actually decoding it. The advantage is that it reduces the processing time, and the disadvantage is that it leads to false positive errors. Then comes the millimeter wave communication, where the communication happens in this particular band of the spectrum 30 to 300 gigahertz band, and this basically millimeter wave communication offers cellular connectivity in this particular band, and particularly for indoor communication where there are dead zones and so on, this is also particularly attractive. The wavelength is typically 1 to 10 millimeter in this millimeter wave communication, and there is a reduced element size and MIMO based narrow beam formation in this particular millimeter wave communication. So, for details of these things I would encourage you to go through this particular paper, which is the Achieving Ultra Reliable Low Latency Communication paper, which has been published in the IEEE Network magazine in 2018. So, here basically you would be able to get a lot more different types of ideas with respect to these methods. Enabling methods include heterogeneous structure, where a single macro cell with multiple small cells would be used, or separate control and data channels could be used. So, separate control channel for microwave frequency, data channel for the millimeter wave frequency, and dual mode small cell. These are some of these different enabling methods that could be used. So, I am talking about these in a very high level, quite fast. I am mentioning these, but if you really have to go through and understand these in detail, a lot more time will be required. So, in case you are very much interested to know about millimeter wave or any of these technologies in much more detail, I would encourage you to go through the corresponding material, the paper, the source that is given at the bottom of the slide. So, disadvantages of millimeter wave communication is that there is a need for high gain and high directional antennas, and there are different other disadvantages such as this technology suffers from high penetration loss and shadowing, and there are many more different other disadvantages. With this we come to an end of this particular lecture, and we have looked at some of these different modern technologies that could be used in the context of industrial communication, particularly with the help of 5G and tactile internet and so on. So, these different newer communication technologies could be used in addition to the IoT communication technology that we have discussed in the first in the first module of this particular course. So, with this we come to an end. Thank you.